Hey, Astro Hub friends! You know gravity, right? It's everywhere, it keeps your feet on the ground, and it holds planets in orbit. But what if I told you this familiar force is also one of the strangest, most mysterious things in the entire universe? We're talking about a cosmic puzzle where galaxies are spinning too fast and huge clusters should be flying apart. It's like there's some invisible superglue holding everything together, but we can't see it. What is this mysterious force, and why is it so hard to pin down? Stick around, because we're diving into some mind-blowing new evidence that's shaking up everything we thought we knew about gravity, and that's what we're unpacking today on Astro Hub. So, we all know gravity, right? It's that familiar force that keeps our feet on the ground and apples falling from trees. But get this, when we zoom out and look at the whole universe, gravity gets super mysterious. I mean, really mysterious. When astronomers gaze at distant galaxies, they see something pretty weird. The stars way out on the edges, the ones farthest from the center, are spinning incredibly fast. Like, way faster than they should be. It's not just individual galaxies either. When we look at huge collections of galaxies, called galaxy clusters, those entire galaxies are also zipping around at speeds that just don't make sense. Now, if the only stuff in these galaxies and clusters was the normal matter we can see, stars, planets, gas, dust, then all those fast-moving stars and galaxies should have just flown apart ages ago. Think of it like a really fast merry-go-round. If you're not holding on tight, you're going to go flying off. But here's the thing. The universe is stable. Galaxies are holding together. Clusters are holding together. It's almost like there's some kind of extra invisible matter out there pulling everything in with super strong gravity. And that, my friends, led to one of the biggest puzzles in science. What in the world is creating all this extra gravity? So, to tackle this huge cosmic puzzle, scientists came up with a pretty wild idea. Dark matter. It's exactly what it sounds like. A type of matter that doesn't shine, doesn't absorb light, and basically doesn't interact with anything we can see or detect. Like, at all. It's not just dark because it doesn't glow like a really faint star. No. It literally has no interaction with light or magnetism or the nuclear forces that hold atoms together. The only way it seems to interact with anything is through gravity. Think of it like this. Imagine an invisible skeleton or a giant unseen hand that's just pulling galaxies and galaxy clusters together, giving them that extra gravitational hug they need to stay stable. We can't see it with our telescopes or even the fanciest detectors we have, but its gravitational effects are everywhere. They're subtly shaping the universe, making sure everything holds together instead of flying apart. For decades now, the hunt for dark matter has been one of the biggest, most exciting quests in science. But even with all our efforts, its true identity is still a complete mystery. We just don't know what it actually is. But what if the whole dark matter idea is wrong? What if we don't need to invent an invisible type of matter at all? Well, some really smart physicists thought, hey, maybe it's not the matter that's weird, but our understanding of gravity itself. They came up with a pretty radical idea called modified Newtonian dynamics, or MOND for short. Instead of adding a new unseen ingredient to the universe, MOND suggests that maybe our trusty old rulebook for gravity needs a bit of an update. It says that when gravity gets super weak, like out in the vast emptiness between galaxies, it might actually start behaving differently than what Newton and Einstein told us. You know how gravity normally works, right? It gets weaker the farther away you get from something. Specifically, it weakens by the square of the distance. So, if you double the distance between two things, gravity doesn't just get half as strong, it gets 4 times weaker. MOND basically says, what if that square rule isn't quite right when we're talking about really cosmic scales? If gravity actually weakened more slowly over those huge distances, then even objects that are super far apart would still feel a stronger pull than we'd expect. That extra pull could be exactly what's holding those fast-spinning galaxies together without us needing any mysterious dark matter at all. It's a pretty elegant thought, isn't it? changing how gravity works rather than inventing something new. To really get a handle on whether MOND or dark matter is the right answer, we can't just look at individual galaxies. We need to zoom out, way out, and see how gravity acts across the entire universe. And for that, we have an amazing tool, the cosmic microwave background radiation, or CMB for short. Think of the CMB as the universe's baby picture. It's literally the oldest light we can detect, a faint glow left over from the Big Bang itself when the universe was just a tiny fraction of its current age. It's like a whisper from the very beginning of everything. Recently, some clever astronomers used a super powerful telescope in Chile called the Atacama Cosmology Telescope, or ACT, to make an incredibly detailed map of this ancient light. This map isn't just pretty, it's a treasure trove of information. By studying this map, we can figure out how huge structures, like those giant galaxy clusters we talked about, are moving around. And those movements, my friends, hold vital clues about how gravity behaves on the grandest, most cosmic scales. So while we're looking at a baby picture of the universe, it's actually telling us secrets about how everything works right now and what forces are truly in charge. So how do we actually use this ancient light, this cosmic baby picture, to test gravity? Well, as this cosmic microwave background, or CMB, light has been traveling across the entire universe for billions of years. It bumps into stuff. Specifically, it passes right through these huge structures called galaxy clusters. Now, these clusters aren't just a bunch of galaxies. They're also packed with super hot, super fast-moving electrons. Think of it like a really dense, gassy cloud around all those galaxies. Sometimes, when the CMB light tries to pass through these clouds of electrons, it actually bounces off them. This bouncing or scattering of the ancient light is what we call the Kinetic Sunyaev-Zel'dovich effect, KSZ for short. It's a bit of a mouthful, but the idea is pretty neat. Here's the cool part. If a whole galaxy cluster is zooming towards us, that scattered CMB light will actually look just a tiny, tiny bit warmer. And if the cluster is moving away from us, the light looks a little cooler. It's just like the Doppler effect you know from sound, where a siren sounds higher pitched as it comes towards you and lower pitched as it goes away, but for light. This KSZ signal from any single cluster is incredibly faint, almost impossible to see on its own. But scientists are clever. By looking at hundreds of thousands of galaxy clusters and combining that KSZ data with other information about the galaxies, they can figure out the average movements of these massive structures. And guess what dictates how these giant galaxy clusters move? You got it, gravity. So, by measuring these subtle temperature changes, we can essentially weigh the gravitational pull between clusters and see how gravity really behaves over mind-boggling, immense distances. All right, so after all that amazing work, what did this cosmic scale gravity test actually tell us? Well, the scientists looked at how gravity weakens over really, really big distances. We're talking from about 30 to 200 megaparsecs. To give you an idea, a megaparsec is over 3 million light years, so this is way, way bigger than even our own galaxy. Now, remember how Newton and Einstein's theories predict that gravity gets weaker by a factor of 2? That's that square of the distance idea we talked about earlier. MOND, in its simplest form, would predict that gravity weakens by a factor of 1 at these huge scales. So, what did the actual data from the ACT telescope show? The results came in with a gravitational weakening factor of about 2.1. There's a little bit of wiggle room in that number, but that's really, really close to 2, and definitely not 1. This is a big deal because it strongly suggests that gravity works pretty much the way we expected it to, even across these mind-boggling cosmic scales. Now, to be fair, some MOND supporters might bring up more complex ideas, like the external field effect, where really big, nearby objects could somehow influence gravity. But honestly, these new findings make it way, way harder for MOND to explain the universe without dark matter. It really seems like that invisible hand of dark matter is still needed to hold our incredible universe together after all.